Hello, Dr. Cos. This will be my 8th time recording this video. For whatever reason, I can't speak today, so yeah. These are the topics I will be covering, and I guess I'll just begin. So the first question is a little different than the standard assessment because the standard assessment gave a graph and asked if it was omic or non-omic, but I figured why not give two and describe which one is omic and which one is non-omic. So omic usually refers to metals, whereas non-omic refers to semiconductors, and omic metals will always have a straight linear relationship, whereas semiconductors have this nice little curve. My first question is, you have a cylindrical 20 ohm, that's supposed to say carbon, I just can't write, carbon resistor of P is equal to, this is just some constant, that is 10 centimeters long, and the cross-sectional area is 100 micrometers squared. The resistor is connected to a 10-volt battery. So the first question asks, find the resistance if the resistor area is halved. So I use this handy-dandy equation for all three parts of this problem, where R is equal to PL over A, R is equal to PL over 1/2 A, since area is halved. So if I didn't solve for this, the resistance would actually be greater since it's divided by less, basically. But I did solve for it, a little cherry on top of the cake, and I got 120 ohms. Here's my math. I just converted my units to meters, and yeah, that's pretty much it. Okay, so B. By what factor does the power dissipated by the resistor change if the resistor length is halved and the battery voltage is halved? So once again, you can see this equation on the left. Resistance is equal to P times 1/2 L, since the length is halved over A. And you might be like, that's nice, but we're not done. Since the resistance is halved and the battery voltage is also halved, and we're trying to find power, we need to go one step further and use this P equals V squared over R equation. So you might say, at first you might think, if something's halved and something else is halved, it's just going to cancel out. But little do they know that V is squared, so this turns into 1/4 over 1/2. So then the power is 1/2. Crazy. The last question for this problem is, by what factor does current change of resistor length and area is tripled and voltage is halved? Now here, length and area, the threes cancel out. Sadly, I canceled out the A instead of the 3 because I'm crazy. So the resistance stays the same. But we're not done yet. So we got our P equals V squared over R equation that we used in the previous problem, and this is going to help us solve for voltage. Now you might be like, we need current, so what are you going to do about that? Crazy. We have another equation where P is equal to I times V. So I'll come back to that. So we solve for our power. I squared, or 1/2 V squared will give us 1/4 over R. I didn't do anything to the R since the R stays the same, and power is 1/4 the original power. So 1/4 power is equal to, not minus, equal to I times 1/2 V. And that's the equation we saw there, right there. Power is equal to current times voltage. So 1/4 our power is equal to our current times 1/2 the voltage, so the current will be 1/2 if all these factors play in. So this, I did it a little different than the standard assessment. I drew my own circuit and I solved using these two lovely rules, which I'll explain, to find each current, or the current running through all of the circuit, and then the voltage drops again across my two resistors, and then the power across my two resistors. So you can see the cute little circuit right there. We've got a 350 ohmic resistor and a 500 ohmic resistor. And you might be like, what do all these symbols mean? Just wait, I'll explain them. So here are our two voltages. I1 is kind of based off of our node rule, where I1 is equal to I2 plus I3. So the current going through here is going to be equal to these plus this, which is why our I1 goes back like this. But here's a little node, an invisible node, one might say, which is why our I2 splits, because we've got our I2 going through this voltage and resistor, and our I3 has to go through this resistor. But never fret, they come back together as I1. We'll come back to this later. We use this to solve for one of our currents. Or I do. I don't know, I keep saying we. Anyways, so another rule I use to find the rest of my currents, I guess, is the loop rule. And you can see they're labeled A and B. You might be like, that's funky. But we've got two loops of current. Because, as I mentioned before, if this is the node, our current is going to go through like this, and it's going to go through like this, because we've got two different voltages. And I set up the loop rule, and you might be like, hey, isn't delta V supposed to equal 0? And I would tell you, yes, it is. And you're going to be like, well, why doesn't it? Well, I times R is equal to V. And so that gives us a voltage. So this is going to be negative 1.5, because when you bring this over and you do the math, as you'll see here, you can solve for I3. And then here I do the same thing. I multiply current times resistance to give me voltage, and I find that I2 is negative 0.0301 amps. And you might say, isn't current supposed to be positive? And I tell you, well, no, it doesn't have to be. This negative means that the actual flow of current is the other way. So instead of the current going this way, it's going this way. Finally, to solve for I1, I used this cute little node rule, and I added up my 0.043 plus negative 0.0301, which is just a minus, and I got positive 0.0129 amps. So those are my three currents, and I used the node rule and loop rule to find them. And then to find voltage across my two resistors, I used VE is equal to IR, and this is for the voltage across the 350 resistor. I just multiplied current across that resistor, across I3, times 350 ohms. Easy enough. And the funny thing, I thought this was really funny when I solved it. Either I'm really bad at math, or this is just a great coincidence. V of 500 ohms, so the voltage drop across 500 ohms is also 15, which I thought was pretty wild. So I hope you find it to be wild too. Finally, to solve for power, I did power across my 350 and 500 ohm resistor, and I used the P is equal to IV equation, which I used on the front page, actually, so connections. And I found that the power is equal to 0.645 watts, and the power across the 500 resistor is 0.45 watts. So this was for circuit 3.4, EPOT 5, and eCirc 5, which I think is just circuit 5. But yeah, I hope you enjoyed my little video. Thank you for watching, and have a good day.